Hello, Math 109 students. This is section 6.2. This section is about two things, one-to-one functions and inverse functions, which we will find out are very related to one another. So what is a one-to-one function? Let's go back to the question of what is a function. Remember that a function is a relation, like all these things are relations, right? A relation just relates one set of things to another set of things. But a function is a special relation where the first set of things we may call the inputs. Each one of those things is only related to one output. So we would say, this is a function because if I were to say, what's the population of Indiana or Washington or South Dakota or any of them, there would be no question, no debate. If everybody's looking at this graphic, everybody would be able to say that the population of Washington at 6.7 million. I don't know if you remember an example we had a couple of chapters ago. It was like, I think it had the number of carats and the diamonds, and some of those carats pointed to multiple different prices because the price of a diamond is not just a function of its size. So that would not be a function because, like, if you had a 1.5 carat diamond, it could have several different prices depending on other factors. So it's not a function of that. It's not perfectly predictable according to the size. All right, so that wouldn't be a function. A one-to-one function means not only is it perfectly predictable according to input, it's also perfectly predictable according to output. So if you know the inputs, you know the output, and if you know the outputs, you know the input. So each input is related to only one output, and each output is related to only one input. Therefore, it's called one-to-one. One input to every one output. So figure 6 would be an example of a one-to-one function. We could ask the question either way and get a perfectly clear answer. Like we could say, what is the population of the state of Indiana, and get 6.4 million? Or we could say, what state has a population of 6.4 million, and we would get Indiana. Figure 7 would not be one-to-one. It's a function because each of these animals has only one life expectancy. But it's not one-to-one because these life expectancies could be associated with more than one animal. So, like if I said, what's the life expectancy of a dog, you would say 11. But if I said, what animal has a life expectancy of 11, you might say dog or you might say cat. So it's not a one-to-one function. Here's a definition. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. Any two inputs correspond to two different outputs. That is, if x1 and x2 are two different inputs of a function f, then f is one-to-one if f of x1 is not equal to f of x2. So the output for x1 is not equal to the output for x2. All right. You can read that if you want some more explanation, but I think we've hit the point enough for that. So let's do this example. Determine whether or not these two relations are one-to-one functions. All right, so part A, it is a function, but it's not a one-to-one function. Why not? Because this output, 38 HDL cholesterol, is associated with two different inputs, 55 and 61. All right, is part B a one-to-one function? Check the inputs first. -2 is associated with only one output because there's no other -2s listed. -1, 0, 1, and 2. There are no repeats of those inputs, right? None of those inputs are listed twice with different outputs. And let's look at the outputs now. 6, 3, 2, 5, 8. Those are not repeated either. So it is one-to-one. All right. What about if we were given a graph? Can we tell whether or not a graph is a one-to-one function easily? Yes, there's a quick way to do it. Just like it's easy to tell whether a graph is a function or not based on the vertical line test, it's easy to tell whether a graph is a one-to-one function by the horizontal line test. So a vertical line test would be if every vertical line would intersect the graph of the relation in at most one point, then it is a function. But if the vertical line crosses it in more than one point, it is not a function. The horizontal line test is similar to that. Here it is. If every horizontal line intersects the graph of a function f in at most one point, then f is one-to-one. So you can see here, this curve here is not one-to-one because the horizontal line test hits it in more than one place, so it fails the horizontal line test. The reason that horizontal line test works is because if a horizontal line hits the graph in more than one place, it means that output, that y value where that horizontal line is, would have more than one input to go with it. Okay? So, using the horizontal line test on example 2, determine whether these are one-to-one functions. Well, f of x equals x squared. Hopefully you remember what that looks like. That's a parabola. A quadratic function is a parabola, like a U shape. So the U shape would not pass the horizontal line test, so it would not be one-to-one. If we thought about it a little more deeply, let's say the output was 4. Well, if x was 2 or if x was negative 2, that would still give you an output of 4. That's why it's not one-to-one. All right, what about g of x equals x cubed? A cubic. Hopefully you remember kind of what a cubic looks like. And a cubic is one-to-one. Let me show you. Help you visualize it better on these graphs. See, the parabola does not pass the horizontal line test, but this cubic function, every horizontal line would only cross that cubic function in at most one place. So it is one-to-one. Let's say you had the output 8. There's only one x value that would give you an output of 8, and it's 2. Negative 2 would give you an output of negative 8. So it would be one-to-one. Every one of those inputs would only have one output, and every one of those outputs would only have one input. All right. Theorem. A function that is increasing on an interval I is a one-to-one function on I. A function that is decreasing on an interval I is a one-to-one function on I. So what we're saying there is if a function increases the entire time on a particular interval, or if it decreases the entire time, like this cubic increases the entire time. It never decreases. The interval of increase is from negative infinity to infinity. It never turns and goes down. And that's always going to happen when it's a one-to-one function. Whereas this parabola, first it has an interval of increase. First it has an interval of decrease from negative infinity to 0, but then it has an interval of increase from 0 to infinity because it has a turn in it. It starts out decreasing, but then it turns into increases. And when that's the case, it's not going to be one-to-one. All right. Suppose that f is a one-to-one function. Then to each x in the domain of f, there is exactly one y in the range because f is a function. And to each y in the range of f, there's exactly one x in the domain because f is one-to-one. The correspondence from the range of f back to the domain of f is called the inverse function of f. The symbol f with this -1 exponent is used to denote the inverse of f. So if you see f with a -1 superscript, you don't say f to the -1. What you say is this is f inverse. That symbol means f inverse. All right. So we're now moving into inverses, and what that has to do with one-to-one functions is only one-to-one functions have inverses that are also functions. If the function is not one-to-one, then I'll show you in a second. It might make more sense after this first example. Find the inverse of this function map right here. It's really, really simple. Indiana points to 6.4 million. Well, in the inverse, it's just going to point the other way. 6.4 million is going to point to Indiana. So all the inverse function does is it reverses the function. So instead of all the states pointing to the populations, it's just going to reverse it, and all the populations will point to the states. In fact, it's kind of like asking the inverse of a question. For the original map here, it'd be like asking the question, what is the population of the state of Indiana? So Indiana would be the input of that question, and the answer or the output of that question is 6.4 million. But we could invert that question the other way and say, what state has a population of 6.4 million? In that case, 6.4 million would be the input of that question, and the answer to that question, or you could say the output of that question, would be Indiana. So the inverse of this function would simply be where these numbers would have arrows pointing back to these states. It's pretty simple. So now let me say again, only one-to-one functions have inverses that are also functions. The reason that would be, let's go back to one that was not one-to-one, and I can show you. This is a function, right? But it's not a one-to-one function. So if we reverse these arrows, then 38 would now point toward two different numbers. It would have two different outputs. Right now 38 is an output that has two different inputs pointing to it. That's fine. It's still a function. But if we reversed it, then 38 would be an input, and it would be pointing to two different outputs and would no longer be a function. So one-to-one functions are the only functions that have inverses that are also functions. All right, so you can see that this is the inverse of the previous problem. Find the inverse of these ordered pairs. Remember that we've said what an inverse does is it reverses the inputs and outputs. So if -3 input has an output of -27, then for the inverse, it's going to have an input of -27 and an output of -3. So we're just going to reverse these, is all we're going to do. So instead of the ordered pair -3, -27, we will now have an ordered pair -27, -3. And instead of -2, -8, it's going to be -8, -2. These next three won't matter because the inputs and outputs are the same regardless. -1, -1, 0, 0, 1, 1. They're reversed, but it doesn't really matter because they're the same. But these next two will matter. This will be, instead of 2, 8, it'll be 8, 2, and this will be 27, 3. So the domain of the original function f is equal to the range of the inverse function. The domain and range swap. And the range of the function f is equal to the domain of the inverse of f. All right, let's look at this. The input x from the domain of f, if you apply f to it so that it becomes now f of x, then if you apply f inverse to that, it's just going to go back to where it was. It's just going to go back to being x again. Because the inverse function completely does the opposite or the reverse of what the function does. The inverse undoes what the function does. Or you could say it the other way. The function reverses the inverse of the function. So if the function ties your shoes, the inverse unties your shoes. If the function unties your shoes, the inverse ties your shoes. Let me show you this a little bit better. Okay, so let's say we have this function f. And let's say x comes into it. And it does something to x so that it becomes f of x when it comes out. Then this inverse function let me make that a little bit better. If you take the output, what just came out of f of x, and put it into the inverse, it's going to undo what just happened, and it's going to end up back where it started. It's going to end up back being x again. So let's say you put, so we'd have the ordered pair, if we had the ordered pair x, f of x in this function, in that, then in the inverse function we're going to have f of x, x. So let's say 5 went into this function, and it came out as a 7. Then put 7 into the inverse, it's going to come back out as a 5. So if you have 5, 7 on that one, you're going to have 7, 5 over here. So another way you could say, you might say, if you have x, y, here, you're going to have y, x here. All right, so another way we could say that is we could say f inverse. You remember in 6.1 we talked about compositions of functions. So if we do f inverse of f of x, that means x goes into f and something happens to it. And then that whole thing goes into f inverse and it undoes whatever just happened. So what are you going to get? You're going to get what you started with. You're going to get x. All right, and you can go the other way as well. F of f inverse of x is also going to equal x for the same reason. All right, and that's what this also says, the same thing. F inverse of f of x is equal to x. And f of f inverse of x is equal to x. So, verifying inverse functions. If we're given two equations, g of x equals x cubed and g inverse of x equals the cube root of x, and we want to verify that those are inverses, then we could do that with what we just said. We could say g inverse of g, which means we got to take one of them and plug it into the other. It doesn't matter which way we go. We could also do g of g inverse. But we got to take one of these and plug it into the other. So let's say if I did g of g inverse. So if I'm taking this one and plugging it into there, so that this becomes the cube root of x. So I'm replacing that x with the cube root of x. So it's the cube root of x cubed. So instead of x cubed, it's the cube root of x cubed. So what happens? The cube root and the cubed exponent cancel each other, and you just get x. And that verifies that they are inverses. Let me show you that you could have also gone the other way on this first example. I'm not going to prove this on the others, but I do want to prove it on this first example just to show you one time. That if you go from here to here, so g inverse of g, so we're plugging x cubed into that spot, so that this is now the cube root of x cubed. What happens again here? The cube root of x cubed, cube root and cube cancels, it's just x. All right, let's do part B. So we have verified it. You don't really have to go both ways. You just pick one way and go. So verify this one. It doesn't matter which way we go. I'm just going to do it this way, but it doesn't matter. You could totally go the other way. Whichever way feels more comfortable to you is totally fine. So instead of being 2 times x, I'm replacing that x with this entire expression, 1/2 x minus 3, and then plus 3. So what happens here? The 2 and the 1/2 cancel, because 2 times 1/2 is just 1. So it's just x minus 3 plus 3, and then minus 3 and plus 3 cancel. So what do you get? You get x. And you have verified that those are inverse functions. They undo each other. All right. This time I'm verifying that these two functions are inverses. So I do the same thing. I will just plug one of them into the other. It doesn't matter which way we go. I think I'm going to go this way, but it totally doesn't matter. I'm going to plug f into f inverse. So that's going to be 1 over, so this is f inverse of f. So it's going to be 1 over x minus 1 plus 1. And so what do? We this 1 over x minus 1, we're going to keep change flip with that thing. So I keep the 1, I change it to multiplication, and I flip the bottom one. The 1 over x minus 1 is going to become x minus 1 over 1. And so then what happens here? Well, 1 times x minus 1 over 1 is just x minus 1 plus 1, and then minus 1 plus 1 cancel. So that's just going to be what? It's just going to be x. So we have verified that they are inverses. Now the next question says, for what values of x is f inverse of f of x equal to x? The reason it asks that is because there may be, especially in this one, there are certain values that are excluded from the domain because they make the thing be undefined. In other words, they make it be 0 on the bottom of the fraction. So for f inverse of f of x, all I'm doing is I'm saying, well, what value can't go in for x? Well, look at f of x. What can't I plug in? I can't plug in 1. So I would say for x not equal to 1. Or if I was going the other way, f of f inverse of x, then I'd look at the domain of that. What can't go into x for f inverse? What would make there be a 0 on the bottom here? 0 itself. So if I went that way, I'd say for x not equal to 0, because I can't plug 0 into that one. All right. There's a certain kind of symmetry between the graph of a function and the graph of its inverse. Let me read it here. The graph of a one-to-one function f and the graph of its inverse f inverse are symmetric with respect to the line y equals x. What is the line y equals x? It's the line that goes diagonally through the origin. Okay, so this is the line y equals x. So a function and its inverse will always be symmetrical about that line. It means if you fold the graph, fold the piece of paper or whatever along that line, that the inverse of a function and the function will fold onto each other perfectly. And that makes sense because since an inverse swaps the x and the y, then it's going to be perfectly symmetrical of when symmetrical from where x and y are the same, y equals x. All right. The graph in figure, example 7, the graph in figure 16a is that of a one-to-one function, y equals f of x. Draw the graph of its inverse. All right, hey, let's do that. Let me get me a different color here. So what I do is I take each one of these points, like -2, -1, and I'm gonna put a new point, -1, -2, where I just reverse those inputs and outputs. So -1, -2 would be right here. And for -1, 0, it's going to be what? 0, -1. 0, -1 is right here. And 2, 1 is going to be the point what? 1, 2, which is right here. All right, let me try to connect those dots to draw that. Oh, that wasn't too good, was it? To draw that graph. And hopefully you can see that this is symmetrical about this line right here, y equals x. Here's the line y equals x. Right, 1, 1, 2, 2, 3, 3, 0, 0, -1, -1, -2, -2. The line y equals x perfectly divides that. So you can see that symmetry. All right, the next concept is how to find the inverse of a function. So if we're just given the equation of a function, f of x, how do we find the equation of the inverse function? It's a pretty neat process. Here are the steps. All right, step 1, swap x and y. 2, solve for y. So once you swap x and y, you've actually already found the inverse of the function in an implicit way. But to make that function be defined explicitly, that inverse function be defined explicitly, then you need to do step 2. So let's do those steps for this function. All I'm going to do, so it's like f of x equals 2x plus 3, I'm going to swap x and y. Now, I guess when I'm saying y, really I'm looking at f of x here, but I'm calling it y because it's just easier to write y than it is to write f of x when we're doing this. So I'm going to put x where the f of x used to be, and I'm going to put y where the x used to be. So I'm swapping the x and the y. So I've done step 1. This is already an inverse, but I want it to be explicitly defined instead of just implicitly defined. So to do that, I need to solve for y. I need to re-solve for y, get y by itself again. And how do I do that? Well, I get rid of this plus 3 by subtracting 3 from both sides. And that gives me x minus 3 equals 2y. Then what? Then divide by 2, and that does it. Y is equal to x minus 3 over 2. You actually would probably see the answer written like this. Instead of writing y, you would see the answer written as f inverse of x is equal to equals x minus 3 over 2. You might also see it written as 1/2 x minus 3/2, which is the same thing as x minus 3 over 2. Now you might also be able to kind of think through that logically and get the same thing. You might say to yourself, well, if this original function, when you put x into it, the first thing that happens is it multiplies it by 2. The second thing that happens is it adds 3. So if I want to reverse that process, that means I got to walk backwards from the way I came. So if the last thing I did was add 3, then the first thing I do in the inverse is subtract 3. Then the thing that I did before that was I multiplied by 2, so the thing that I do after that is to divide by 2. So that's the kind of the logical way. Hopefully that makes some sense to you. The next thing it wants to do is to graph f and the f inverse on the same coordinate axes. All right, we could do that by hand, or we could do it in our calculator. I guess I'll do it by hand real quick. So let's see. 2x plus 3 up 2 over 1. Something like that. 1/2 x minus 3/2. So negative 1.5 is the y-intercept. Now go up 1 over 2. So there's the inverse. I'm not drawing that too neat, but you can kind of see that it has that symmetry about line y equals x. Or if we did it on our calculator, all right, I went ahead and typed in 2x plus 3, and then here I'm going to type in, this is how you can get a fraction bar. I don't know if I've shown you this already, but you hit alpha and then F1, which is the green option above the y equals. So the alpha is what gets you there. And then the first option is a fraction bar. There's probably another way to do this too, but that's one way. So I believe we said x minus 3 over 2. And let's see what these look like. I've got to zoom back to my standard zoom window, and now we can see them pretty well. All right, this example, they want me to find the inverse of this function. So again, I'm going to swap x and y. So everywhere that I have an f of x, I'm going to put x. And everywhere that I have an x, I'm going to put a y. So x equals 2y plus 1 over y minus 1. So the first thing you should do here, if I'm trying to get y by itself, is I want to get everything off the bottom. So I'm going to multiply by y minus 1 on both sides. That's going to cancel that y minus 1 so that it's off the bottom. I'm going to go ahead and distribute that x. So that's going to give me xy minus x equals 2y plus 1. Now get your y terms, get any term that has a y in it on the same side. So I'm going to move my 2y over here. So that gives me xy minus 2y minus x equals plus 1. Or just equals 1. Now if a term does not have a y in it, move it away from the terms that have a y in it. So I'm going to add x to both sides. That's going to give me, I'm going to write up here, xy minus 2y equals 1 plus x. Or let me just write x plus 1 instead there. X plus 1. Now, I want to get y by itself. This may be a trick that you wouldn't think of, but what I will do is I will factor out a y from both of these terms. Because these terms both have a y in common, I'm going to factor a y out. And that leaves me with x minus 2 when I do that. Maybe you can predict the next step to get y by itself would be to divide by x minus 2. So that's it. So y equals x plus 1 over x minus 2. Or we would probably see it written as f inverse of x equals x plus 1 over x minus 2. All right, then it says check the result. What you'd have to do to check the result is you'd have to plug what we just found into x right there and right there. Or you could go the other way and take this and plug it into x there and there. And you would then simplify as much as possible and get it down to, it should just come out to x when you simplify everything. And if it doesn't, then something's wrong. But it should. I'm not going to go through that process because I don't think it's necessary, because we've already shown you how to do stuff like that earlier in this video. So let's go on to example 10. Finding the inverse of a domain-restricted function. Find the inverse of y equals f of x equals x squared if x is greater than or equal to 0. Graph f and f inverse. Why does it say that? Why does it say if x is greater than or equal to 0 for this particular function? It's because x squared is not 1 to 1. So that function does not have an inverse that is a function. So they have to restrict the domain, restrict it to a particular portion of the graph where it is 1 to 1, where it will be 1 to 1. So if you just, in other words, if we just look at x greater than or equal to 0, it means we're just looking at the right half of the parabola. So the right half of the parabola, if we just eliminate the left half, would be a 1 to 1 function on that interval. So all you have to do is exchange the variables x and y. So just put the y where the x was and the x where the y was. So look how they wrote it. They wrote instead of y equals x squared, they wrote x equals y squared. And then resolve for y, get the y by itself. You would do that by taking the square root of both sides. And when you do, you would just get y on the right and the square root of x on the left. You'd actually get plus or minus the square root of x, wouldn't you? But it said to restrict it to where we're only looking at the where x is greater than or equal to 0. All right, so f inverse for that thing would just be the positive square root of x. So here is that graph. The right portion of x squared is right here in blue. And the inverse of that, the square root of x, is here in pink. And you can see, based on the symmetry, that they look like good inverses of one another. All right, that does finish us up for section 6.2. Good luck on the assignment. There's one assignment that combines 6.1 and 6.2 together. So good luck on that one. I will see you again in the other sections of chapter 6.